So one thing that we talked about yesterday, right, was the magnetic force between two parallel current carrying wires, right? We did a problem where we had to figure out what those forces were, and we saw that we had an equation, but maybe it wasn't clear where that equation comes from for the force per length between these two wires. So let's start by saying that we recall that the B field, or the magnetic field, from one wire, from a long wire, is the magnitude we got when we did the Biot-Savart law the other day, mu naught I over 2 pi times A, where A is the distance you are from the wire. Right, and then the direction. So if we have the current going this way, the direction of the magnetic field looped around it like this. This is all stuff that, and I'm not drawing the full loops just because to show that these lines are going behind the wire, but we know that they're there. Okay, I think I can stop there. But so, and remember, there's kind of a shortcut right-hand rule. If you put your thumb in the direction of the current, your fingers kind of will curl around in the direction of the loops around the wire. All right. So now let's look at another. So let's call this one I1. This is our wire 1. So let's find the force that this wire feels, right, from the magnetic field from B1. So what is the force on wire 2 from wire 1's magnetic field? Right, and then if we know Newton's third law, we'll realize that the opposite is going to be true as well. The force from wire 2 on wire 1 is going to be the same. So let's say we'll call this distance here is A, right? This lowercase a, because this is how far the magnetic field at this point is from wire 1. All right, so far. What other equation am I going to need that we derived this week?
You're gonna need the force equation,
Yeah, we're going to need a force equation, right?
which is the B field times the current.
Yeah,
current
just about, right? We know that the force on a wire is going to be the current in the wire, right? That's I2 times the L cross B we had, right? Was our, where L is the length of the wire and the direction in the direction of the current, and B is the magnetic field. So
we need L in case it's not infinite.
Well, what we're going to do is let's force per unit length, right? If we double the length of these wires, the force between them is going to be twice as strong. So what we want to do is we're going to divide by L and get the force per unit length of the wires. So the length of the wires isn't going to actually matter for that. And remember, these loops that I drew in here, just to show kind of the direction, they're not the only, right? The loops, there's an infinite number of them, right? And they're all centered on the it's hard to draw magnetic field lines. They're all centered on the first wire, but there's even there's still a magnetic field all the way out here, right, where wire 2 is. It's weaker than the magnetic field in closer because A is bigger. But we do know that their magnetic field from wire 1 points into the page at this point. right? And that's from this one, right? Once we get down to the area below, you know, on the y-axis, the B field is into the page here. Right, and we talked about that earlier in the week, so I don't want to go through again why. I mean, it is just the right hand rule. But is that clear? Are there questions about why the magnetic field from this wire at this point, wire 2, is into the page? Okay, so so now we can figure out, well, we can see the
Wait a second. Is wire 2 going in the same direction as wire 1?
that's a good question. Yeah, we'll say the current is in
The
the same
current.
direction. Yeah.
Okay, sweet. All right.
And then we'll take a look at what happens when they're in opposite directions as well. But yeah, we'll start with they're the same direction. All right, so the magnitude of the force. So let me do so the magnitude of the force is just current 2 times the length of the wire times B, right? There's no the perpendicular. We do know that the B and L are perpendicular here, so we're not going to have a sine of any angle. So this is going to be I2 times L times the magnetic field, which is mu naught times I1 over 2 pi A. Right, so we have both currents in here, right? The current 2 because from the force equation, and then current 1's in there because current 1 affects how strong the magnetic field is. So what I get for the force, I'm going to divide out the length. So the force per unit length, right, dividing both sides by L, is just equal to mu naught times currents over 2 pi A. And I think that was the form that we used this equation in yesterday.
I have a question, Mr. Marcus, about this. Does that equation cover the force on wire 1 on wire 2 and 2 on 1? Or is it just what?
Yeah. So right now, what we calculated was the force from wire 1 on wire 2. But we know that from Newton's third law, if one body exerts a force on another body, the other body exerts an equal and opposite force on that body. So wire 2 is going to have to exert an equal force on an opposite force on wire 1. And you could do that. We would see you would get the same things even if we started over. And we found that we can see that the B field for wire 2 is going to be out of the page up here, right? That this one makes, but we're still going to get the same. We would just basically we would have the exact same equation, except the I1 would be here and the I2 would be there, right? So we would have the same value.
No, but like my question is, does that equation cover that Newton's third law, or does it or do you have to multiply by 2 or something?
No, you don't have to multiply by 2. No, this is each of these two forces. This is what this equation really is the force per unit length of on wire 2 from wire 1. And then we can use Newton's third law to say, and the force from wire 1 or the force on wire 1 from wire 2 is going to be exactly the same. So we can either say that using Newton's third law or just by doing this again and trading the labels.
Okay.
So maybe it'll be, let's make sure if we look at the directions, maybe that'll be a little bit clearer, right? What's the direction of that force? Right, so let's do the right hand rule, right? L is to the right here, and B is into the page. So that means the force is upwards towards the top of the page. So from the right hand rule, that's the direction of the force of wire 1 on 2. I'll say 1 on 2.
Wait, I could have sworn. Hold up, can you do that right hand thing again?
Yep. So
Because I did it and I got
fingers
left
to the right.
Right.
L,
Yeah.
the direction of
Yeah.
the current. Then cross B. B is into the page. So I curl my fingers down towards into the page. And then my thumb points in the direction of the force. So to the top of the page in the plus Y direction. So that means wire 2 is going to be attracted to wire 1 and be pulled upwards.
Right. I mixed up the B. Okay, sweet.
Yeah. And we can see that the force of 1 on 2, well, we know Newton's third law, right, is going to say the force of 2 on 1 has to be downwards with this same magnitude. But we can see that also because if we think about the magnetic field, now I've drawn in the magnetic field from 1, right? These loops here and these into the page marks here are the magnetic field from 1. But I2 is going to make us a similar magnetic field. I mean, if it's the same current, it'll make the same magnetic field. And above it here, the magnetic field will be coming out of the page. So if I wanted to find out the force on current 1, well, current 1, if I point my fingers to the right and then curl them out of the page, my thumb points downwards. So I get a downwards force. So the force from 2 on 1 is downwards, right? And these are equal and opposite. Right, and that's Newton's third law. Right. So what we can say is that if the currents are in the same direction, and if force 2 feels an upwards force and 1 feels a downwards force, that means the wires attract. Are we okay with that? We can see that the wires are attracting because current 2 feels an upwards force, current 1 feels a downwards force. And then we can also say, well, let's look now. Let's switch the direction of I2. So what happens if the currents aren't going in the same direction? So now the magnitudes, nothing here changes. The magnitude is the same. But now when I try the right-hand rule, instead of my I2, my L starting to the right, I have to have my L to the left. My magnetic field here is still into the page. So now I get a downwards force. Right. So I see that if the current is in the opposite direction, they're going to be repelled from it. The force is a repellent force. All right. And that's because, well, we get the opposite answer from the right-hand rule if one of the factors is flipped, one of the vectors is flipped. So let me put a box around this. That's kind of the big result, right? The magnitude of the force per length of 2 wires that are both carrying a current, right? It's proportional to both of the currents, inversely proportional to how far apart they are. And then we also saw that if the 2 currents are flowing in the same direction, the force is attractive. The wires, are pulled towards each other. If the currents are in opposite directions, then the wires are going to repel. Any questions or thoughts about that? All right.